with Mr. Thomas.
Hello there! Here we go, Chapter 6, Lesson number 10, the MacLaurin Series 1. If you are just looking for examples on the MacLaurin series, you may wish to skip forward to example 1 because there are a few slides explaining what MacLaurin series is all about. So if you want to skip that, go for it. If not, here we go with the MacLaurin series. What is it all about? Well, let's say you've got a geometric series 1 plus x squared plus x cubed and so on. We can see here that our common ratio, to go from 1 to x, we're multiplying by x. Also to go from x to x squared, again you're multiplying by x. Because you're multiplying by x every time, that will be your common ratio. And we can say that that geometric series has a sum to infinity if the common ratio x is between -1 and 1. And if it is, then using the formula from the last lesson, that sum to infinity will be 1 over 1 take away x. So what we can say then is that if you add all the terms of this series, the 1 plus the x squared plus the x cubed and so on, and you keep on going, what you will get, using your knowledge of sum to infinity, you will just get 1 over 1 take away x. Let's think about rewriting this. If we rewrite this 1 over 1 take away x, well, we could move that bottom line up to the top, put brackets around it, move up to the top, and it goes to the power of -1. So we can say then that this 1 plus x squared plus x cubed, as well as being equal to 1 over 1 take away x, well, if you rewrite that, you can rewrite that as 1 take away x to the power of -1. It's really just the same thing. So really our function f of x equals 1 take away x to the power of -1 can be expressed as an infinite series of the form a constant plus a constant times x plus a constant times x squared plus a constant times x cubed and so on. And we call those constants a0, and then a1, and then a2, and then a3. So really we get a0 plus a1x plus a2x squared plus a3x cubed, and so on. And really, we can express our function as an infinite series if the value of x is between -1 and 1. Really, that is true for any function. Any function can be expressed as an infinite series of that form. a0 plus a1x plus a2x squared plus a3x cubed, and so on. And really, these values of a are just going to be constants. If you do that, then it is known as expressing your function f of x as a power series, or a MacLaurin series, named after the Scottish mathematician Colin MacLaurin. Well, hello there, everybody. Check out my funky do. It is important, though, to know that power series only converge for certain values of x. Let's look at that a little more. So say we are expressing our function as an infinite series. Really, we've got these constants, a0, a1, a2, a3, a4, and so on. How could we find the values of these constants, the coefficients really of your x and x squared and so on? How could you do it? Igor, help us out. Perfect! We can find the values of these constants by replacing x with 0. If you do that, well, you'd have f of 0, which means then that you would have, if you replace x with 0, a1 times 0, which is just 0. a2 times 0 squared, which again is 0. a3 times 0 cubed. That's just all going to be 0, and apart from this a0. And it means then, if you have f of 0, that will be the value of a0. But how could you work out the other values? a1, a2, a3. Igor, keep on going. What could you do? Differentiate! Perfect! You can differentiate. So really you can find the coefficients of your x and x squared and x cubed and so on by evaluating the function f of x and its derivatives at x equals 0. So let's say we do that. Then if we work out f of 0, we'll get a0 plus a1 times 0 plus a2 times 0 squared and so on. In other words, as I said, we just get a0 plus a load of zeros, which is just a0. So in other words, a0 equals f of 0. If we take the first derivative, so f dash x, and we differentiate, well, because a0 is a constant, that is going to disappear. a1 times x, if you differentiate that, it will leave you just with a1. If you differentiate a2 x squared, you will get 2a2x. And really, if you replace x with 0, well, that's just going to make that term all 0. And it's going to be the same with an x, an x, an x. So you'll just be left with a1. So in other words, a1 is going to be f dash 0. Working out the second derivative, f dash dash x, f double dash x, then if you differentiate again, well, you're differentiating this line. And if you differentiate a1, well, it just goes to 0. Differentiate 2a2x, well, 2a2 will just stay there and x will disappear. So we've got the 2a2. If we differentiate 3a3x squared, well, the 2 is going to come down, so we'd have 6a3x, and so on. And we're replacing the x with 0, so that's going to disappear. And again, the next term will also disappear, and the next one will disappear. So really, the second derivative will leave us with just 2a2. How do we get the value of a2 then? Well, we can divide both sides by 2. So really, a2 is going to be the second derivative when x is 0 over 2. We can keep on going and following this pattern. We can take then the third derivative. So differentiate that second derivative, that is what you will get. Replace x with 0. All these terms with an x will go to 0, leaving us with 6a3. To get the value of a3 then, well, you're just dividing by 6, or really the 3 times 2. To get the fourth derivative, well, you just differentiate again, and you can keep on going, and you can follow that pattern. So you've got the fourth derivative, you're replacing x with 0. So really, you would have 4 times 3 times 2 times a4. To get a4 on its own, well, you've got the fourth derivative when x is 0 over the 4 times 3 times 2. And so on, you can keep on going. If you're still awake and you're still with me, then you will see that if you go back to this magical formula just up here, f of x equals a0 plus a1x plus a2x squared, and so on, and you replace a0, a1, a2, a3 with these values that we have found, then we come up with this. So f of x equals f of 0 plus f dash 0x plus f double dash 0 over 2 factorial, because remember it was over 2 and you can write 2 just as 2 factorial, that's just 2 times 1 multiplied by the x squared, plus the third derivative when x is 0 over 3 times 2, well, you can write that again as just 3 factorial, 3 times 2 times 1. And then again you've got this part here, you've got the fourth derivative when x is 0 over the 4 times 3 times 2. Again, you can write that as 4 factorial. And again, you've got this x to the power of 4. This is used to find the MacLaurin series of a given function. So let's try some examples. Example 1. Find the MacLaurin series for the function f of x equals e to the power of 2x, up to and including the term in x to the power of 4. So the first thing we're doing is we're starting off with f of x. F of x equals e to the power of 2x. We know that. But if we're wanting the term in x to the power of 4, this here is the formula that we are wanting, and we have to find the first derivative and the second derivative and the third and the fourth derivative to get that x to the power of 4. So we're going to work out f dash x, then f double dash x, triple dash x, and then the fourth derivative as well. So differentiating e to the power of 2x, how would you do that? Perfect. E to the power of anything just stays as it is. But then what you have to do is multiply by the derivative of the index. Differentiate 2x, you get 2, so it would be 2 e to the power of 2x. Differentiate again, so the second derivative. Again, anything, e to the power of anything just stays as e to the power of whatever it is. But you multiply again by the derivative. So we'd have 2e to the power of 2x, and we're multiplying again by 2, which will give us 4e to the power of 2x. Differentiate that, it will stay as 4e to the power of 2x, but again you multiply by the derivative, so we multiply by that 2, and that'll give us 8e to the power of 2x. And for the fourth derivative, differentiate this, well, it's 8e to the power of 2x. Multiply again by that derivative, e to the power of anything stays as it is, the 8 will stay as well. Multiply it by 2 though, and we will get 16 e to the power of 2x. So we have found the first, second, third, and fourth derivatives. We now have to replace x with 0. So f of 0 is going to be, well, that's e to the power of 2 times 0. So in other words, e to the power of 0. And anything to the power of 0 is just going to be perfect. That is just 1. Work your way through this and work out f dash 0, f double dash 0, and so on. So f dash 0, well, that's 2 times e to the power of 2 times 0, 0. So it's still e to the power of 0, so it's still 1. So it's just 2 times 1, which is 2. After that, we'd have 4 times e to the power of 0 again. So it's just 4 times 1, which is 4. This here would be 8 times e to the power of 2 times 0. So it's 8 times 1, which is 8. And here 16 times e to the power of 0, which is going to be 16 times 1, which is 16. Using this formula here, f of x, well, f of x was e to the power of 2x. That is going to be f of 0. Well, f of 0 is 1, so it's going to be 1 plus f dash 0 is 2, so it's going to be 2 times x. Plus f double dash 0, f double dash 0 is 4, so that's going to be 4 over 2 factorial. 2 factorial is just 2 times 1, which is 2. So it's going to be 4 over 2 multiplied by x squared. We can keep on going. The third derivative, f triple dash 0 is going to be 8. So that's going to be 8 over 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So we're going to have 8 over 6. And then x cubed. The fourth derivative, when we replace x with 0, was 16. So that's going to be 16 over 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on. Really, you could keep on going. You could work out the term with x to the 5 and x to the 6, and so on. But we just want up to and including the term in x to the power of 4. So we can stop there. Just include the wee plus, ... because you know it is an infinite series. After that, just simplify it. So the 1 will stay as it is, 2x will stay as it is, 4 over 2 just goes to 2, so we'd have 2x squared, 8 over 6 becomes 4 thirds x cubed, and the 16 over 24 would go to 2 thirds x to the power of 4. So that is the MacLaurin series for e to the power of 2x. Yeah. Example 2, find the MacLaurin series for the function f of x equals cos 2x up to and including the term, once again, in x to the power of 4. So to do this, again, we are starting with our f of x. f of x is cos 2x. If we're wanting the term in x to the power of 4, we're going to have to go through and differentiate. So we want to work out f dash x, f double dash x, and so on. So working them out, f dash x, if you differentiate cos 2x, well, that will go to, cos goes to negative sign, so we'd have negative sine 2x. But remember, imagine the 2x has brackets around it. So you are wanting to multiply by the derivative of what would be in the brackets. So we'd have negative sine 2x times by 2. So in other words, negative 2 sine 2x. For the second derivative, we once again differentiate that. Remember though, again, you have to apply the chain rule. So negative 2 sine, if you differentiate that, will go to, well, you could keep actually the negative 2 outside. So keep that as negative 2 times. Differentiate sine, that will go to cos. So you'd have cos 2x. And once again, because you've got the brackets here, you'd multiply by 2. So you'd have the negative 2 times the derivative of sine 2x would be 2 cos 2x. So in other words, negative 4 cos 2x. Differentiating again, well, the third derivative, keep the negative 4 just outside, differentiate cos 2x. Differentiate cos 2x, well, we've just done that up here, that's negative 2 sine 2x. So it's negative 4 times the derivative, which is negative 2 sine 2x, which is 8 sine 2x. Differentiate that, 8, I'm just keeping as it is, and differentiating sine 2x. Differentiate sine 2x, and that will give you 2 cos 2x. Multiply the brackets, and you get 16 cos 2x. We have the fourth derivative here, but we now have to work out f of 0 and f dash 0, f double dash 0, and so on. So f of 0 is going to be cos of 2 times 0. So in other words, cos of 0, which is just going to be 1. Think about your cos graph. If you think about the cos graph, it looks something like that. So at 0, it's going to be up at 1. Work out f dash 0. F dash 0 is going to be negative 2 sine 2 times 0, so negative 2 sine 0. And once again, you can think about your graph. If you think about your sine graph, well, that is just going to be at 0, it's down at 0. So it's negative 2 times 0, which is just 0. Work out the double dash 0, and that will give us negative 4 times cos of 0, which is negative 4. F triple dash 0 is going to give us 8 times sine of 0, which is 0. And the last one there, you're going to have 16 times cos of 0, which is going to be 16 times 1, which is just 16. So we have differentiated and worked out f of 0, f dash 0, and so on. So we can say then that cos of 2x equals, well, f of 0 is just 1, we can see that, plus f dash 0 is just 0, so it's going to be 0 times x. So really, we don't need to write that. F double dash 0 is negative 4, so we've got negative 4 over 2 factorial, so negative 4 over 2 times 1, which is just 2, multiplied by this x squared. Plus f triple dash 0 is 0, so we've got 0 over 3 factorial, multiplied by x cubed. And for the last one, that worked out to be 16, so we've got 16 over 4 factorial. So 16 over 4 times 3 times 2 times 1, which is 24, multiplied by x to the power of 4. Again, this is an infinite series. You've got plus and then dot, dot, dot to show it's going to keep on going. Simplify that though, so the 1 will stay as it is. This 0x, you don't need to write that. The negative, you can put that to the front, and 4 over 2 is just 2, so let's take away 2x squared. 0 over 6 multiplied by x cubed is 0, so you don't need to write that either. And then 16 over 24 goes to 2/3. And x to the power of 4 will stay as x to the power of 4. So that is you writing cos 2x as an infinite series. You're finding the MacLaurin series. That is what you would have. Example 3, find the MacLaurin series for the function f of x equals ln, and in brackets, 1 plus 3x, up to and including the term in x to the power of 4. So for this one, again, you are starting with your function f of x equals ln, 1 plus 3x. You know you are going to have to go on and differentiate, so work out f dash x and double dash x, etc. So doing that, f dash x, if you differentiate ln something, it goes to 1 over the something. So we'd have 1 over 1 plus 3x. However, that would not be the end, because in the brackets we've got an x term, and you have to multiply by the derivative of that x term. So it would give us the 1 over 1 plus 3x, but we'd have to multiply by the derivative, so we're multiplying by 3. Move that to the top of the fraction, so it's 3 over 1 plus 3x. In order to differentiate this though, rewrite it all in one line, just makes it far easier. So keep the 3 as it is, put brackets around this 1 plus 3x, move it up to the top line, so it'll go from 1 plus 3x to the power of 1 to the power of negative 1. To work out the second derivative then, you would differentiate this. So bring the power down, so negative 1 times 3 is negative 3, keep the 1 plus 3x as it is, and then decrease the power by 1, negative 2. However, always remember you have to multiply by the derivative. So if you differentiate 1 plus 3x, you still get 3, so multiply by that. Therefore, you've got the negative 3 times 3, so you've got the negative 9 just at the start. And in brackets, 1 plus 3x to the power of negative 2. To differentiate that, negative 9, you're bringing this power down, so that's going to give you 18. Keep the brackets as they are, decrease the power by 1, and again multiply by the derivative, so multiply by the 3. 3 times 18, that'll simplify to 54. Differentiate that, again bring the power down, so negative 3 times 54 is going to be negative 162. Keep the brackets as they are, 1 plus 3x to the power of, decrease the power by 1, and again multiply by the derivative of what's in the brackets, multiply by 3. After that, you've got 3 times the negative 162, so that's negative 486. Keep the brackets as they are, and then you've got this negative 4. So that is us with the fourth derivative. You know from there you have to work out f of 0 and f dash 0 and f double dash 0 and so on. So f of 0 is going to be, well really for that you're going to have 3 times 0, which is 0, so you're just going to have ln 1. ln 1 is going to be, brilliant, you got it, it's just going to be 0. f dash 0 is going to be, well, if you imagine replacing x with 0 in here, you'd have 1 plus 3 times 0, which is 0, so really it's just 1 plus 0, which is 1, so you've got 1 to the power of something. 1 to the power of anything is just going to be 1, so it's just 3 times 1, which is 3. You could also think about rewriting this as 1 to the power of negative 1, but move that to the bottom underneath the 3, so I'll go to 3 over 1 to the power of positive 1, which is 3 over 1, which is just still 3. Doesn't matter which way you think about it, as long as you get the right answer. Work out f double dash 0, so negative 9 times 1 plus 3 times 0, which is 0, so that's just going to be 1 plus 0, which is 1. 1 to the power of anything is just 1, so it's negative 9 times 1, negative 9. Keep on going, so you've got 54 times, that works out to be 0 as well, to the power of 1 plus 0 to the power of negative 3, so it's just 1 to the power of something, leaving you with a 54. And after that, if you keep on going, you're going to have negative 486 times 1 to the power of negative 4, which is just negative 486. Use that formula once again, so you've got ln 1 plus 3x, that is our function, and if you express that as an infinite series, you can say that is equal to, well, f of 0 is just 0, plus f dash 0 worked out to be 3, so it's 3 times x, which is 3x. You would then have negative 9 over 2 factorial times x squared, which is negative 9 over 2 x squared. The third derivative, when x was 0, you'd add 54, so it's 54 over 3 factorial times by the x cubed, so it's 54 over 6 x cubed. And then you've got negative 486 over the 4 factorial multiplied by x to the power of 4, which gives you negative 486 over 24, x to the power of 4, plus dot dot dot. Again, it's your infinite series, so make sure you include that to show that it's going to keep on going. Simplify that though. 0 you don't need to write, so you're starting off with the 3x. Bring the negative to the front. Keep that as 9 over 2x squared. You've got this 54 over 6, which works out to be 9x cubed. Put the negative again to the front, and 486 over 24 simplifies to 81 over 4, x to the power of 4. And that will be your answer for that one. Woo! Last example in this lesson 1 of MacLaurin expansion. Example 4, find the MacLaurin series for the function f of x equals the square root of 1 plus 4x, up to and including the term in x to the power of 4. So we're again starting with this function. We have to work out its derivatives, and to differentiate the square root of 1 plus 4x, what we have to do is rewrite it as 1 plus 4x in brackets to the power of 1/2. We can now differentiate that dead easily, because all we do is bring the power down, so that will be 1/2 times 1 plus 4x to the power of, take 1 off, so 1/2 take away 1 is negative 1/2. But again, you multiply by the derivative, so differentiate what's inside the brackets, you get 4, so we're multiplying by 4. 4 times 1/2 just simplifies to 2. So it's 2 times this 1 plus 4x to the power of negative 1/2. Differentiate again, so get the second derivative, bring the power down, so 2 times this negative 1/2, which is negative 1. Keep the brackets as they are, take 1 off, so negative 1/2 take away 1, negative 1 take away 2 is negative 3, so it's negative 3 over 2. Multiply by the derivative, differentiate 1 plus 4x, it's 4. So now we've got negative 1 times 4, which is negative 4. Bracket, 1 plus 4x, close bracket, to the power of negative 3 over 2. Differentiate that, bring the power down once again, so you've got negative 4 times by the negative 3 over 2, which is positive 6. Keep the brackets as they are, take 1 off the power, negative 3 take away 2 is negative 5, so it's negative 5 over 2, and multiply by the derivative. So 1 plus 4x, differentiate it, you get 4, so we're multiplying by that. 4 times 6 gives you the 24. From there, differentiate again, so negative 5 over 2, multiply that by 24, and you get negative 60. So negative 60, keep the brackets as they are, take 1 off the power, negative 5, take away 2 is negative 7, so negative 7 over 2, and again multiply by this derivative, so multiply by the 4. Negative 60 times 4 is negative 240, bracket 1 plus 4x, close bracket, to the power of negative 7 over 2. We have worked out the first, second, third, and fourth derivatives. Woo! But now we have to work out f of 0 and f dash 0 and f double dash 0 and so on. So f of 0 is going to be 1 plus 4 times 0, To the power of a half, well, 4 times 0 is 0, so it's just 1 to the power of a half. 1 to the power of anything is just going to be 1. After that, work out f dash 0. So f dash 0 is going to be 2 times 1 plus 0 to the power of negative 1 half. 1 to the power of anything is just 1, so it's going to be 2 times 1, which is just going to be 2. After that, we're going to have 1 plus 0 again, which to the power of something. 1 to the power of anything is going to be 1, so it's negative 4 times 1, which is just negative 4. 24 times 1 plus 4 times 0, so it's just 1 plus 0, so it's just 1 to the power of negative 5 over 2. Again, you could rewrite that if you want. Write it as 24 over 1 to the power of positive 5 over 2. Work out 1 to the positive 5 over 2. It just works out to be 1, so you've got 24 over 1, which is just 24. And this one as well, negative 240 times 1 plus 0 to the power of something. 1 to the power of anything is just 1, so it's negative 240. After that, to get the Maclaurin series, you are using this formula. It is given on your formula sheet. F of x equals, and so on. So f of x is the square root of 1 plus 4x. So that would be f of 0 is 1. So it's 1 plus f dash 0 times x is going to be 2 times x. Plus f double dash 0 over 2 factorial times x squared would be negative 4 over 2 factorial times x squared. After that, this is 24, so it's 24 over 3 factorial. 3 times 2 times 1, which is 6 times x cubed. And then this is negative 240, so it's plus negative 240 over 24, which is the 4 factorial, over times x to the power of 4. Simplify that then, that becomes 1 plus, keep the 2x just as it is, negative 4 over 2, we'll put the negative to the front, that works out to be 2, and then you've got this x squared. 24 over 6 goes to 4, and you've got this x cubed, and then put the negative to the front, and that simplifies to 10x to the power of 4. Again, make sure you've got this plus, and then dot 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 to show it is your infinite series. That is 4 examples there with Maclaurin expansion, Maclaurin series. Once you have mastered these, move on to the next lesson where I look at slightly trickier examples, or possibly there's a part B where you have to do something else. Try these questions in Unit 2 booklet, pages 32 and 33. Check your answers as you go. Have fun. Best of luck. Woo! Bye! Maclaurin series. Yeah.